All right. The recording is live, so the first 5 minutes weren't recorded. We also did another practice question on balancing chemical equations. Here we saw that there are 3 hydrogens on the left. After balancing, there are 3 hydrogens on the right. The same thing can be said for both the sodium as well as the chlorine. There is an equal number on both sides. But one of the key factors of the second practice question was the use of PO4. You should be able to recognize PO4 as a polyatomic ion. It's phosphate, which means when we balance it, we consider it an entire unit. In other words, we do not split up the phosphate into 1 phosphorus and 4 oxygens. That does lead to a much more complicated attempt to balance. Whenever dealing with polyatomic ions, we consider them as a single unit. After balancing reactions, we then introduced the concept of state symbols and solubility. State symbols that we covered, of course, are solids, liquids, and gases. To identify what's a solid, you will use your periodic table. The legend will tell you if something's a metal or a non-metal. To know what are gases, these are our traditional common diatomic elements, such as hydrogen, nitrogen, oxygen, fluorine, a bunch of others that I'd mentioned in a previous class. And the other one that may not be immediately rememberable is CO2, carbon dioxide gas. Now, we also have the state symbol of water, liquid, L. Now, in addition to the 3 state symbols, we also introduced a new type, aqueous. Now, the term aqueous refers to the fact that most reactions, especially Chem 300, they take place in water. In other words, when we say that something is aqueous, what we're saying is that it is dissolvable in water. An example of this is table salt, sodium chloride. We know, of course, that table salt is a solid. However, it is dissolvable in water. That's the same as soluble in water. For that reason, we give it the term AQ. Compare this to something like a strip of magnesium metal. Magnesium metal will not dissolve in water, so it is given the term solid. So since we know what gases are, and we know that the only liquid we'll really be dealing with in this class is water, the question now becomes, how do we tell the difference between a solid and an aqueous species? I mean, it's one thing to remember, oh yeah, of course I know that table salt is dissolvable, but what if I were to give you something else? That's what then gave rise to our solubility rules table right here. I'll remind you all that you will be given this reference sheet as part of your exam. So you do not need to memorize it, but you do need to know how to read it and use it. It's meant to be read from left to right, following the columns and, of course, the rows. So take, for example, if the compound contains a NO3, a nitrate, then it is aqueous, except when bonded to, well, there are no exceptions in this case right here. Similarly, if the compound contains an OH, a hydroxide, it is solid, except when bonded to one of these ions. With that, we were able to introduce state symbols to the reactions we already covered. Just taking a quick example right here, H3PO4. You have 2 ways to go about it. You can talk in terms of PO4. If the compound contains a PO4, then it is solid, except when bonded to a group 1 cation, which is what hydrogen is. Hence, it is aqueous. You also could have approached it from the perspective of the hydrogen. If the compound contains a group 1 cation, then it is aqueous, no exceptions. So in principle, no matter which ion you use, you should lead to the same answer. There are some occasions, however, where only 1 ion is on the table. For example, sodium chloride. There is a chlorine on the table, and it is on you to remember that sodium is a group 1 cation. All of this is to say that this solubility rules table is what will tell you if something's a solid or aqueous species. That then led to our discussion of reaction archetypes. And reaction archetypes are what allow us to predict products. The first archetype we went over was synthesis, 2 or more chemicals combining into 1, generically represented here as A plus X to give us AX. This is the most standard form of reaction. 2 elements are coming together. Sodium and chlorine, for example, come together to form sodium chloride. Hydrogen and chlorine come together to form hydrogen chloride. But the key point here is now that we understand the basics of balancing as well as state symbols, all of those factors must be included. We can see in the first equation, there are 2 sodiums on the left, 2 sodiums on the right, 2 chlorines on the left, and in total, 2 chlorines on the right. In addition, we also have state symbols. Sodium by itself is an element, so you have to refer to the periodic table. It's a group 1 metal, so it's solid. Cl2 is a diatomic element, so it's a gas. And we just talked about how sodium chloride is aqueous. The opposite of synthesis is known as decomposition. Some resources or websites online sometimes refer to it as decay. They mean the same thing. In essence, this is the opposite to synthesis. Whereas in synthesis, 2 chemicals come together to combine, in decomposition, a single compound breaks up into its individual chemicals, shown here generically by AX breaking up into A plus X. Since we've already described this as the exact opposite to synthesis, we can do a couple examples right down here, where if I zoom out, you'll notice that it's just the opposite direction of the synthesis reaction previously seen. Following that, we then talked about combustion. Combustion involves hydrocarbons. These are molecules of the formula CXHY, where X and Y can be any number, will react with oxygen to always form carbon dioxide and water. So regardless of the type of hydrocarbon made or used, CO2 and water will always be your products. There's no real guesswork here. Of course, it's on you to remember that CO2 is a gas. It's on you to remember that water is a liquid. So whenever I ask you a combustion question, really and truly what I'm testing for is the balancing. That then led us to our discussion on double displacement. This includes chemical compounds full-on swapping partners, shown here generically with AB plus CD, swapping such that A ends up with D, and C ends up with B. Shown here in the reaction below, sorry. Shown here in the reaction below between sodium chloride and lithium fluoride, we can see that the partners do swap. Sodium ends up with fluorine. Lithium ends up with chlorine. While we were on this topic yesterday, I talked a little bit about why we write CB and not BC. The reason is simple. The cation is written first, then the anion. So let's say, for example, you forgot this principle on the exam, and instead of writing LiCl, you wrote ClLi. You wouldn't get this wrong per se. You just see a frowny face on your exam. It's not wrong, it just looks really, really weird. Our discussion on double displacement then led to our discussion on single displacement, where the stark contrast is one element replaces another. Shown here generically with A plus BC ends up with AC plus B. In other words, A has replaced B, AC comes together, and B is left by its lonesome. We saw a couple examples where in the case of sodium reacting with lithium chloride, the sodium replaces the lithium to form sodium chloride. Now, of course, it should make sense why the sodium replaces the lithium specifically. The simple answer is they're both cations. Cation will replace cation. In the same vein, if we had another element that we know to eventually become an anion, it will replace the other anion, in this case, fluorine. We also had situations where we dealt with a transition metal, such as zinc added to copper sulfate. Like replaces like, so zinc replaces copper. And we end up with zinc sulfate and copper. But the thing about transition metals is that we cannot just look at the periodic table to identify its charge. There has to be some information given to us to help us. Since zinc replaces copper, presumably it also takes on its charge. The copper we know is 2+, so the zinc will also become 2+. All of this information that we've gotten so far is what really helps us answer the very simple question, provide a complete balanced equation with state symbols for the reaction shown below. I even went so far as to tell you that each reaction will be worth 3 points, and I've broken down what the 3 points come from. Now, to predict the products of a reaction, there are steps to be followed in order. The first thing we're going to do is identify archetype. In this case, we quickly recognize that we were dealing with two chemical compounds, AB plus CD. That's what tells us this will be a double displacement. Based on the archetype, we're then going to match ions, then crisscross is needed. This is the point where most students fail to remember that these steps are meant to be followed in order. More often than not, when I see that students are making mistakes on their exam or worksheets, it's because they've jumped from number 1 to number 3 just to go back to crisscross and back to match ions. This will lead you to an incorrect answer. It will be frustrating and it will be wrong. So first, we're going to match ions. We know based on the archetype that we'll end up with AD plus CB. Sodium ends up with fluorine. Barium ends up with chlorine. Then we would crisscross as needed. Sodium is in group 1, so it has a positive 1 charge. Fluorine is a negative 1, so they would crisscross to be 1 to 1. NaF is correct as written. When we apply the same logic to the barium chloride, barium is 2 plus, chlorine is negative 1. Crisscross tells us we will end up with BaCl2. Hence why it's important to keep track of your charges. Now that we've matched ions and crisscross as needed, finally all we need to do is balance the reaction and indicate state symbols. This is something we've already talked about so far, so I'm not going to go back into too much detail about it. Now, picking up for today's lecture, we're moving on to our next topic under reactions. This is what's known as subcategories of reactions. Now, previously we talked about reaction archetypes. Reaction archetypes are what allow us to predict products. But subcategories represent labels that we assign to reactions after the fact. For example, the first one we'll talk about is gas evolution. In gas evolution, a gas is formed. So take, for example, the following reaction between, let's say, magnesium solid and HCl aqueous. All right, first we're going to predict products. Remember the steps. The first thing we're going to do is identify the archetype. We have a single element reacting with a compound. So this means this will be A plus BC leads us to AC plus B. How do I know specifically that the magnesium will replace the hydrogen? They're both cations. Like replaces like. Based on this, now I'm going to match ions. I end up with AC, MgCl, plus B, which is just hydrogen. I have not crisscrossed yet. I have not balanced or put state symbols on the product side. I've simply matched ions. Now we're going to crisscross as needed. Zooming into the product side, we should remember that magnesium in group 2 has a charge of 2 plus. Chlorine in group 17 has a charge of negative 1. Crisscross tells us that the 2 is going to get swung down, the 1 is going to get swung down, leading to MgCl2. For the hydrogen, even though it does not have an anionic partner to crisscross, it is on you to remember that hydrogen is a diatomic element and will always form H2. With that, we have matched ions and crisscrossed as needed. Now we're going to balance. 1 magnesium, 1 magnesium. 1 hydrogen, 2 hydrogens. Oh, that's a problem. That's unbalanced. There's 2 on the right, but only 1 on the left. No big deal, though. We'll just put a 2 on the left. In doing so, we'll have balanced the hydrogen, and the magnesium is already balanced. Finally, we have 2 chlorines on the left. Oh, and would you look at that? We have 2 chlorines on the right. One of the key points behind balancing is that normally, I would say pretty much all the time, by the time you finish balancing each chemical, everything will be done for you. All that's left is state symbols. Hopefully we all have our solubility rules in front of us or near us. Magnesium chloride, the compound contains a chloride. By default, it is soluble. Is magnesium an exception? No. So MgCl2 is aqueous. And then hydrogen, it is on us to recognize that as a diatomic element, it's a gas. With this, we now identify this reaction as being a gas evolution reaction. We did not know it was gas evolution heading into it. Well, of course, technically, I'm the one doing the lecture notes. I knew it was going to be gas evolution. But the only way we can assign that label is after we do the state symbols. We form a gas evolution. As a reminder, the gases that you are expected to know off the top of your head are the classic diatomic elements, such as H2, N2, O2, F2, Cl2, and carbon dioxide. Now, under gas evolution, there is a very special chemical that we encounter. We're going to talk about the curious case of H2CO3. Taking a reaction here between sodium carbonate and HCl, let's spend a few moments trying to predict the products of this from scratch. First things first, identify the archetype. We have here a couple chemical compounds, so this will most likely follow double displacement. AB plus CD gives us AD plus CB. We're going to match ions first. AD is NaCl, CB is HCO3. All I have done is matched ions. I have not started balancing. I have not started crisscross. Do note 2 important things. The CO3 gets carried over. That number 3 does remain the same because it's a polyatomic ion. It moves as an entire unit. The 2 in sodium does not automatically carry over because sodium is not a polyatomic ion. Now that we've matched ions, now we're going to crisscross as needed. Sodium is +1, chlorine is -1, no crisscross needed. Hydrogen is +1, carbonate is -2. That's what tells us we will be crisscrossing. This answer is actually H2CO3. Products predicted, ions matched, crisscross done. All that's left is to balance and include state symbols. 2 sodiums on the left, 1 sodium on the right. Easy fix. Just put a 2 in front of the NaCl. 1 CO3, 1 CO3. 1 hydrogen, 2 hydrogens. Okay, that's a problem. To balance it, we just put a 2 in front of the HCl. So now the sodium is balanced, the carbonate is balanced, the hydrogen is balanced. 2 chlorines. Oh, and would you look at that? 2 chlorines. Now, something special happens to H2CO3. Whenever H2CO3 is formed, it will always decompose into H2O and CO2 gas. Whenever H2CO3 is formed, this will always happen. So the reaction I've written up above is technically incomplete because, as I just pointed out, this will decompose. So our final answer, our actual reaction, is as follows. Sodium carbonate reacts with hydrogen chloride, and that results in sodium chloride, water, and CO2 gas. It is on each student to recognize that this is the correct answer. If I were to give you this question on the exam and you left it with this up here, this would only be given a 2 out of 3. You need to recognize that this breaks down into H2O and CO2 to get the full 3 out of 3. This is also considered a gas evolution because CO2 gas is formed. Next up, neutralization. In the case of neutralization, water and an ionic compound is formed. Ionic, it's been a while since we've heard that term way back in nomenclature. Let's not forget, ionic compounds are defined as a metal and a non-metal together. Of course, this might sometimes include transition metals. So let's take an example right here. We have the reaction between sodium hydroxide and HCl. I'm not going to spend too much time working through the steps of the products. Hopefully you should be understanding how I get these. The products are sodium chloride and HOH. I've purposely left off the state symbols for that last one. Confirm for yourselves that this is the correct product. Now, HOH is something you should be able to quickly recognize as being identical to H2O. They're the same thing. So you can write whichever form you want on the exam. They're both correct. Since it's water, it's given the state symbol liquid. So we know this is a neutralization reaction because water is formed and an ionic compound, a metal and a non-metal. Finally, we have precipitation. In precipitation, a solid product, henceforth referred to as the precipitate, is formed from non-solid reactants. So the solid product is given the term precipitate. So precipitation leads to a precipitate. An example of this is as follows. Silver nitrate reacting with sodium chloride. This is a double displacement reaction. A, B, C, D to give us AD plus CB. The products are silver chloride and sodium nitrate. According to the solubility rules table, all NO3 compounds are soluble, very first row. All of them are soluble, no exceptions. In the case of chlorine, chlorines are traditionally aqueous, except when bonded to, and silver is an exception. So this is solid. So we see here that we result in a solid from non-solid reactants. That is the key defining factor of precipitation. If one of these reactants happen to be solid already, this is no longer precipitation. This is just a regular reaction. Precipitation is marked by the fact that a solid product is newly formed from non-solid reactants. I see a hand. No, only solids. Oh, you meant like from the non-solid side? Yes. These can be gases, this can be liquid. It just cannot be a solid. Good question. So do note the primary difference between the archetypes we've covered and the subcategories we went over today. The archetypes are what allow us to predict the products of a reaction, and the subcategories are labels that we assign after predicting products. We see that a gas is formed, hence this is gas evolution. In the other cases with neutralization and precipitate, we know what the products should be. Do we have any questions before I move on? Okay. Our final topic under the big heading of reactions is called ionic equations. Ionic equations is not a new archetype. It is not a new subcategory. Ionic equations are simply a different way to write reactions focusing on chemical changes. Ionic equations are a different way to write reactions with a focus on chemical changes. There are steps required of us for ionic equations. The steps are again to be followed in order. They are as follows. Number one, first, you will write the complete balanced equation. And when I say complete, I mean products and state symbols. Upon writing the complete balanced equation, you will then write the complete ionic equation. To get the complete ionic equation, we will break apart aqueous species only. So the only one that will be affected by writing the complete ionic equations will be aqueous species. You will leave the others alone. In other words, we will not break solids, liquids, or gases. Aqueous is all that matters. Once we do that, we will then identify and eliminate all spectators. All right, that's a new word right there. Spectator is being used in this class, in this context. It becomes important for us to understand what a spectator is. A spectator is an ion that does not change state. After step 4, we will then write the net ionic equation. Don't worry, we are going to do a couple examples of this. Here's a question. Provide the net ionic equation for the reactions below. Very first one is aluminum added to copper chloride. And that's what the question would look like. Oh, I'm so sorry. What's your question? To the steps? Oh, I see. Okay, yeah. Okay. Provide the net ionic equation for the reactions shown below. The first one we're working on is aluminum added to copper chloride. Let's get our steps at the ready. The very first thing we are going to do according to our steps is write the complete balanced equation. To do that, we need to predict products, balance, and include state symbols. So let's take a second. We have here a single element replacing something in a compound. This is, of course, single displacement. We have A plus BC. Think to yourselves, take a guess internally. What is A going to replace? The aluminum is going to replace the copper. Why? Because they're both cations. The end result, of course, is AC plus B. Matching ions, this leads us to AlCl plus copper. All I've done so far is matched ions. Now I'm going to crisscross if needed. Looking at the individual products, starting with copper. Copper is by itself, so it's not in a compound, no crisscross needed. It's fine as is. Aluminum in group 3 has a +3 charge. I'm sorry, in group 13. Aluminum in group 13 has a +3 charge. Chlorine in group 17 has a -1 charge. This what tells us that the 3 is going to get carried down, the 1 is going to get carried down, leading to AlCl3. Now that we've matched ions and crisscross as needed, we'll take a second to balance the equation. 1 aluminum on the left. I don't know why the screen's a little slow today. I apologize for that. 1 aluminum on the left, 1 aluminum on the right, 1 copper on the left, 1 copper on the right. So everything so far is balanced. 2 chlorines on the left, 3 chlorines on the right. So chlorine is not balanced. So we need to put some number in front of these guys to make them equal. So what we're going to do is we're going to say 2 times 3 is equal to 6. We're going to aim for 6 chlorines total. What number do I need to put in front of the copper chloride to get 6 chlorines? 3. 3 right here, and a 2 in front of the AlCl3. And we're done, right? No. Why? We've messed up the aluminum and copper, so we got to start from scratch. 1 aluminum, 2 aluminum. Easy fix. Just put a 2 in front of it. 3 copper, 1 copper. Easy fix. Just put a 3 in front of it. We've now balanced the equation. All that's left is state symbols. Aluminum chloride is aqueous. Chlorines are aqueous. Aluminum is not an exception. And copper is a transition metal. So copper is a solid. Insofar, we have completed the first step. Write the complete balanced equation. Next, it says to write the complete ionic equation, we are going to break up all aqueous species. We will ignore solids, liquids, or gases. So here's what that looks like. Let me just label it, the complete ionic equation. From left to right, we start with aluminum. Aluminum is a solid, so we leave it alone. Next, we have copper chloride. In this case, copper chloride is aqueous, so we are going to break it up. This is 3 copper plus aqueous, 6 chlorine minus, also aqueous. Take a second to understand that this is what I mean by break up. Sorry, this should be a 2+ right here. Don't worry, I'll talk about how we knew it was a 2+ in a second. But this is what I mean by break up. The word is ionic equations. We break them up to see what the ions are. We break up copper chloride to clearly show us copper 2+. We break up chlorine to get us Cl-. They're both aqueous, so we recognize that. What about the balancing? Well, there was a 3 in front of it to begin with. That tells us there are 3 copper ions. Similarly, there are 3 times 2 chlorines for a total of 6 chlorine ions. You may be wondering, well, Supreet, why didn't we write 3Cl2? Well, remember, this is ionic equations. We're trying to get the ions. There is no such thing as Cl2 minus. This does not exist. So this would be incorrect. It's more appropriately 6 chlorine ions. Now, here's a good question. How did I know that the copper was 2+? Does anyone want to take a guess? I see a hand. Ryla, is that? From the crisscross, we're able to say that reverse crisscross tells us the 2 is going to get swung up to 2+. All right, keeping it going. On the product side, the first one we have is aluminum chloride. Aluminum chloride is aqueous. This is what tells us this will break up into 2Al3+, 6 chlorine minus, aqueous. Yet again, the same principles are followed. An aqueous species is broken up into its ions. The balancing is kept consistent. The state symbols are shown. And to be very, very clear, the charges are also shown. Next, we have copper, which is a solid, so it's left alone. This is the complete ionic equation. It shows everything that can be made. With that, we have completed step 2. The next step says to identify and eliminate spectators. These are ions that do not change state over the course of the reaction. Now, the reason they're called spectators is not a coincidence. I liken them to the audience at any sort of athletic game. The audience in the stands are not themselves playing in the game, but their very presence helps the players play better. So the ions, the spectator ions, are the ones that are basically on the sidelines, not doing anything. They don't change states. So let's look through the reaction to try to identify which ones are spectators. From left to right, we're starting with aluminum. Aluminum starts solid, it ends up aqueous. This is a change, it participates, we leave it alone. Copper starts aqueous and ends up solid. We leave it alone. Chlorine starts aqueous and ends up aqueous. This does not change, hence it is eliminated. It does not participate in the reaction itself, but its presence helps it along. With that, we have identified our spectator ions. The last thing we need to do now is write the net ionic equation. The word net, of course, is used to make it clear that we're writing the final version of it. The net ionic equation is as follows. We have 2 aluminum added to 3 copper 2+ aqueous, resulting in 2 Al 3+ aqueous added to 3 copper solid. And as you can see, the chlorines have been eliminated entirely. It is still the same reaction that we've been focused on from the very beginning, but now we're only focused on the important bits, the chemical changes. It's not a new type of reaction. It's not a new subcategory. It's just a different way of writing it. And here's why this method is so useful. As we know, chemicals cost money. So let's say, for example, that as a solid, as a pure solid, copper costs $1,000 as a pure solid copper metal. Now, you as a researcher can go purchase $1,000 worth of copper, write it in your budget, your spreadsheet, and move on with your life. However, what if a chemist realized, hey, aluminum costs $500 and copper in this form, the copper chloride, costs $250. You see, what this tells us is instead of buying $1,000 worth of copper, we can buy $750 of these reactants and make copper solid, saving us $250. This is the importance of ionic equations. They allow us to focus on important changes in a reaction that allow us, in the grand scheme of things, to save money. It's cheaper to spend $750, have a grad student run the reaction, make the copper solid. Now all of a sudden you have a surplus of $250 that you can purchase other stuff with. So ionic equations come from a place of necessity and reality for research. In its entirety, this question would be worth 5 points. It would be 3 points for the correct balanced equation, and it would be 2 points for the net ionic equation. Remember that normally I will not see your scratch work. Scratch paper is yours to keep. And I can tell you on the exam, this is what the question is going to look like. Provide the net ionic equation. Do we have any questions so far? No? Okay. Let's try a couple more. The first one we're going to do is the reaction between calcium hydroxide and sodium nitrate. What I would like for everyone to do right now is do step 1. Provide the complete balanced equation, and then we will go through the ionic together. So right now over the next, it's 12:18, take 3 minutes, predict the products of this reaction, balance it, and include state symbols. After 3 minutes, we will go through the ionic equation process together. If you have any questions, raise your hand and I'll just come right to you. Take another minute and a half. Remember, you have the steps to predict the products. Just refer to that part of your notes and follow the steps. Okay, 1222. The correct products balanced with state symbols are calcium nitrate, sodium hydroxide, with balancing 2 in front of the NaOH and a 2 in front of the NaNO3. Check your answers against what I wrote. What's your question?
Should it be CaOH2 or no? Because OH is negative.
Thanks for catching that. You have identified a small mistake. There should be a CaOH2. I apologize for that typo. That doesn't count as a point because it's not a content thing. It's just I forgot to write the 2. Okay. Now that we have that, let's do the ionic equation. You have the steps at the ready. The first thing we're going to do is we're going to break apart all aqueous species to get the complete ionic equation. We're not going to break apart the calcium hydroxide because it's a solid. We are going to break apart the sodium nitrate because it's aqueous, leading to 2Na plus 2NO3 aqueous. On the product side, we have calcium 2 plus, 2NO3 minus, and then, of course, 2 sodium plus, 2 OH minus. Now that we've written the complete ionic equation out, aka we've broken up all aqueous species into their ions, we're going to look and identify our spectators. As a reminder, spectator ions are those that do not change state over the course of the reaction. Starting from left to right, calcium starts off solid, it ends up aqueous, we leave it alone. OH starts off solid, ends up aqueous, we leave it alone. Sodium starts off aqueous, ends up aqueous. This is deleted. NO3 starts aqueous, ends up aqueous. This is deleted. The net ionic equation overall is calcium hydroxide breaking up into calcium 2 plus and 2 OH minus. Again, this entire question would be worth 5 points on the exam. Note a couple of things that I am looking for when I grade this. For ionic equations, for net ionic equations, I am looking for correct breakups. I'm also looking for correct charges. Meaning if you forgot to write the 2 plus here, I'd probably take off half credit. If you forgot all of the charges, I would take off a full point. So I need to know that you clearly recognize what is being broken up and what the charges are. As you'll note, when writing the complete ionic equation, it can get really congested really quickly. So sometimes on my practice problems, I'll say specifically, no state symbols are needed in the ionic equation, just to reduce congestion. Let's do another one. We have zinc solid added to copper sulfate aqueous. Right now, just as before, I'd like everyone to predict the products of this reaction, balance it, and include state symbols. We will go through the ionic part together. Let me just confirm I didn't miss a number. Correct, it's good, looks good. Take about 3 minutes to do that. If you have a question, just raise your hand and I'll come to you. Less than a minute. All right, 12:30 by my clock. The answer you should have gotten for the products is zinc sulfate, aqueous, and copper solid. No further balancing needed, and the state symbols are just aqueous and solid. Now we're going to break up aqueous species to get the complete ionic from left to right. Zinc is left alone because it's a solid. Copper sulfate breaks up into Cu2+ and SO4 2-. On the product side, the zinc sulfate is now aqueous, so we have zinc 2+. Hey, how did we know it was 2+? It took the place of copper, and we know that copper is 2+. Good job. Zinc is aqueous. Sulfate is 2- aqueous. And then copper is left alone. Going through one by one to identify spectators. Zinc starts solid. It ends up aqueous. It's left alone. Copper starts aqueous, ends up solid. It is left alone. Sulfate starts aqueous, ends up aqueous. This is eliminated. This is what tells us that the final answer, the net ionic equation, is zinc added to copper 2+, gives us zinc 2+ and copper. This is the net ionic equation for the reaction given. Do we have any questions so far? All right, we're going to do one last one together. I'm going to do it for you from scratch. We have the reaction between sodium carbonate and HCl. Hopefully we're getting the hang of things. We're identifying archetypes. You should be able to recognize this as being a double displacement. So they're going to swap. We end up with sodium chloride and HCO3. Now I'm going to crisscross if needed. Sodium is +1, chlorine is -1, so that's fine. Hydrogen is +1, carbonate is -2. Okay, so just put a 2 right after the H. Now we're going to balance it. 2 sodium, 1 sodium. Let's put a 2 in front of it. 1 carbonate, 1 carbonate. 1 hydrogen, 2 hydrogens. Let's put a 2 in front of the HCl. 2 chlorines, 2 chlorines. All we have left is our state symbols. Sodium chloride is aqueous. We've talked about that at length today. H2CO3 is also aqueous. And from here, we can start the ionic equation, right? I see a couple heads shaking no. Who wants to say why not? What do I need to do? I see a hand in front. The compound on the far right breaks down into H2O and CO2. So actually, I need to erase it and write it correctly this time. Plus H2O liquid plus CO2 gas. Now to write the complete ionic, as always, we're going to break up aqueous species. This becomes 2Na+, CO3 2- plus 2H+, 2Cl- to give us 2Na+, 2Cl- plus H2O plus CO2. I have purposefully dropped the state symbols from the complete just because it can get really congested and may need 2 lines. So I'm just ignoring it for right now to make it clearer to read. Now that I have the complete ionic equation, I'm going to go piece by piece to identify what has and has not changed. Even though the aqueous symbol is no longer there, I can identify what has changed based on the charges. We see sodium plus on the left. We see sodium plus on the right. This stays the same. It is eliminated. We see CO3 2- on the left. And technically, it exists in both H2O and CO2. This is a pretty clear-cut change, so it's left alone. Hydrogen starts off H+, and it ends up part of H2O. This is very clearly a change. It is left alone. Chlorine starts -1. It ends up -1. This does not change, hence it's eliminated. The result is CO3 2 minus aqueous added to 2H plus aqueous to give us H2O liquid and CO2 gas. Do note that now that I'm back to the net ionic, which is a lot shorter, I'm putting back the state symbols. I am okay if you drop the state symbols in the complete because I understand it can get really congested, but your final answer should have it. And that's it. Do we have any questions? I see a hand in front. I heard the first part. You asked, why did I put 2 in front of the sodium? And then? Does any brave soul want to answer her question for me? Why did we put a 2 in front of the Na plus? Because it's not a polyatomic ion. There are 2 sodiums. So there's 2 sodium ions. CO3 is a polyatomic, so it's its own unit. So there's only 1 CO3 instead of there being 3. Polyatomic maintains its subscripts. Good question and good answer for that student who volunteered. Any other questions on this?
So the polyatomic always keeps the subscript?
Yes.
So if it's not polyatomic, it keeps the subscript number, but if it's not polyatomic,
It does not keep it, correct.
so you would have to add a bigger 2, right?
Correct. Any other questions? Yeah, here in the back.
So why would we like 2H, for H2O and CO2?
What were you asking?
Like why those subscription? Those polyatomic ions. So
No, so back when so this was that curious case. I'll just go back to that specific one right here. So remember back when we did this, we recognized that the actual product is H2CO3, but that will always split into H2O and CO2. So those 2 and 3 isn't a reflection of polyatomic, it's a reflection of this guy being broken up. There's a lot to keep track of in this topic. When we meet tomorrow for lab, we have a dry lab tomorrow workshop. Please be sure to bring your periodic table, your solubility rules, your common polyatomic ions, because all of that information will help you. We're going to end lecture for today as I have nothing else to teach. Good luck. I'll see you tomorrow. If anyone has any questions, come talk to me after class. Have a good day.
I don't believe it's better.
yes, but like I'm imagining if we weren't getting water.
I don't have any but yeah, from this
Like that was, yeah, I